this first one, and for almost all of these, your function is going to be in terms of an integral. That's what I was teaching you last time. This is your accumulation function. All right, so we have f of x equaling that thing. It says, where is f of x a minimum? All right, maximums and minimums come from critical points, and that is derivative equals 0. So we're going to get the derivative and set it equal to 0. All right, so for this one, we're going to need a chain rule because there's more than just x there. So I usually just go ahead and put that on first. So the derivative of this will be 2x minus 3. And then you're just going to take this statement and plug it in for t. So it's e to the power of all of that stuff squared. And again, we're setting it equal to 0 for critical points. Now the e to the stuff you actually get to ignore. E to anything, it's going to be an asymptote at 0. It's going to be a swoop and it will not ever actually touch 0. So all we end up with is this part, which greatly simplifies things. And so you're going to add 3 and then divide by 2. So 3 halves, and so that one is C. All right, number 2, which of the following is an antiderivative of this? What you kind of need to do is just check each choice, and it's going to be C, D, or E. It's going to be one of those ones that has the integral in it. You would take the derivative of each of these and see which one gives you this f of x. And it's going to end up being E. If you just take this x and plug it in for t, then you get this statement right here. Now, the other ones, if you take what's there and plug it in, you'll get this as well, but they would involve a chain rule. Like this one would involve chaining on the derivative of that. You would end up with, this times a 3x squared. Here, you would end up with, same thing. You would have to multiply on a 3x squared, which you don't have a 3x squared out front here. It's just this statement. So it cannot be either of those. So that one is E. All right, number 3, we're given this graph of f. Differential function f is shown. Let h be given by this accumulation function, accumulation starting at 0. And we're going to compare h of 2, h prime of 2, and h double prime of 2. So the function, the derivative, and the second derivative. All right, so if we do h of 2, that's your accumulated area from 0 to 2. Now, I don't know exactly how much area that is. It's not a shape that I can find the area of, but I know it's above the sea level, so I know that this is positive. Whatever amount it is, I know it's a positive amount. It's the area from 0 to 2. All right, and then when we do h prime, we do h prime of x here, you're just going to plug x in for t. So that's going to be f of x. So that is this actual graph. And so if we plug in 2 to that, we get this point right here, which is 0. So this is we can actually get that one. That one equals 0. And then when we do the second derivative of h, that's going to be the first derivative of x. So looking at this graph, this is the graph of f. If we do the derivative, that means slope of a tangent line. So we would be looking at the slope of this graph at 2. And so if you look at the slope of 2, if I draw in a tangent line, it would have a negative slope. So again, I don't know exactly, I'm not going to put an equal sign, I'll put an arrow because I don't know exactly what that amount is, but the slope at 2 is negative if I draw in a tangent. So if we're putting these in order smallest to biggest, it's going to be the negative one, so that would be the second derivative, and then 0, so that would be the first derivative, and then the positive one, so that would just be the actual function. So putting them in order, we want the second derivative, and then the first derivative, and then the function. So that one's going to be E. I like questions like that because it makes you tie together integrals and derivatives. Like it puts it all together in one question. So you need to know your stuff to be able to answer something like that. All right, so number 4, we're just doing the derivative of this. Now there's going to be a chain rule. You have to chain on the derivative of 2x, which would just be 2. And then you're going to take 2x and plug it in for t. And so we're just going to cube the stuff that's in the parentheses there. So this would be 2 ln 8x cubed plus 1. So that one is D. All right, number 5 is the same thing. We're just doing the derivative of this. So again, there's going to be a chain rule. We have to multiply on the derivative of square root of x, which will be 1/2 square root of x. And then you just take square root of x and plug it in for t. So this would be 1/1 plus, now the square root and the squared would cancel, so that'll just end up being x. And then what they did is they put this together in a single fraction. So it would be 1, these would be multiplied together. So it would be 1 over all of that stuff. So 1/2 square root of x, and then times 1 plus x. So that one is going to be a. All right, number 6. I know I'm going to need a calculator for this because look at all these decimals. Right? Function f is given by this. What is the average rate of change? All right, I'm going to throw this question at you guys. Hey guys, what does average rate of change mean? Just in a single word, what is average rate of change? Like, what are they asking us for? Good, nice job, perfect. Slope. All right, average rate of change just means slope. Regular old algebra 1 slope from 0 to 3. So I'm going to need a point for 0 and a point for 3. And here's where the calculator comes in. We are going to have to plug 0 and 3 into this function, which involves an integral. So this is math 9. Again, math 9 is going to be your best friend during this unit. All right, so we want to plug in 0 for x. So this is going to be from 1 to 0, square root of, now I know it says t, but I'm going to type x just because it's convenient. I have an x button. And then you have to put, oh, whoops, not there. You have to put an x at the end for the dx. So I'm just plugging 0 in for x for the function. And that's going to be some crazy decimal. What I'm going to do is store that. Oh, right, so what I'm going to do is store that. So you're going to hit your store button, which is right down here at the bottom. It says stow. It's going to put a little arrow on there. And I'm going to store it as A. So you hit alpha A and then enter. So store alpha A, enter. And what that's going to allow me to do is like a copy paste. So I have that stored as A. Now I want to do the exact same thing and plug in 3. So here's the fastest way to do this, because again, the AP exam is timed. You want to cut down time whenever you can. I'm just going to go up and bring back this integral and just go and change the 0 to a 3. So I just hit the up arrow. I went and brought that back. I changed the 0 to a 3. I'm going to hit enter, and that gives me my output for 3. So I'm going to store that one as alpha b. So I'm going to do store alpha b. And if you look at the green letters above all of these, you have access to the whole alphabet. I just typically use A and B for everything, or C if I need to. Normally you would have to store that many things, but I just use A and B because it's convenient. They're right next to the alpha key. All right, so we plugged those in. I stored them as A and B. And now we're going to do our slope. So sloping these points, it would be b minus a over 3 minus 0. And so I'm just going to type that in. Get the fraction bar. We'll have b minus a over, well, 3. You can put minus 0 if you want. And that will give you your final answer. That's your slope. So it was a lot of button pushing. We didn't really do like a whole lot of work by hand. But you did have to know that it meant slope, and you did have to be able to use math 9 for that problem. And so that one is E. All right, so this one, I can't remember if you were allowed a calculator for this one or not, but I'm going to allow it because, for heaven's sake, look at this function. And I think they would have allowed it for this one too. I can't remember. I can't memorize every one, but I'm going to allow a calculator for this one because that function is kind of crazy. All right, so let G be this function. Which of the following statements must be true? And then they start talking about increasing and decreasing. All right, so well, actually, I was going to pull out my stick-it note, but I'll just write it down. If g of x is increasing, that means the derivative is positive. If g of x is decreasing, that means the derivative is negative. So let's find the derivative of this, g prime of x. And all you're going to do, there's no chain rule because it's just an x. You're just going to plug x in for all of these t's here. All right, so I'm going to type this in the calculator, and we're going to look at where it's positive and negative, so above and below sea level. All right, so I'm going to go to y equals, and I'm going to type in this. Sorry, that glare is really bad. Let me move this over here. So I'm going to type in that. So 100 parentheses x squared minus 3x plus 2 close parentheses e to the power negative x squared. And I'm going to hit zoom 6 just for standard. I may need to change that, but we'll just start with standard. And let's look at what, oh, that's good enough. I think I might need to zoom in on that little part. We'll see what's happening. But Roman numeral 1 says G is increasing from 1 to 2. That means this graph should be above sea level from 1 to 2. Well, here's 1 and here's 2, and it looks like it's below sea level, so that is not going to be true. So we do not want that one. And even just from that, you can start narrowing down your choices. Like anything that has a Roman numeral 1 in it, you can get rid of. So if you can even get through like one Roman numeral, you can narrow down your choices. All right, increasing from 2 to 3. That means we want this graph to be above sea level from 2 to 3. That's really, really small. Let me zoom in on that part of the graph. Let's see. From 2 to 3. So that's from here to here. And it looks like it's above the x-axis from 2 to 3. Okay, so that one's going to be good. We want that one. So actually that lets us get rid of C as well. So as you go through these, you can keep on narrowing down your choices. And then G of 3 is bigger than 0. All right, well, let me go back to the home screen. Let me quit out of here. I'm just going to plug in 3 for x and see what I get. So this will be math 9. I'm going to go from 1 to 3, and then I'm going to have to type all this again. So 100 parentheses x squared minus 3x plus 2 close parentheses e to the negative x squared, and then dx at the end. So I just plugged in 3 for this x. I just did math 9, plugged it all in, and I got a negative result. So that is not above 0, so we do not want this one. We only want Roman numeral 2, and so that is B. All right, number 8. Here's our function, f of x equals all of this. We want to know where the graph is concave down. All right, so concave down is when the second derivative is negative. All right, so let's get our first derivative, and then we'll get our second derivative, and we can see where that's negative. So first derivative, there's no chain rule because this is just x. You're just going to plug x in for all of these t's. Oops, that's a cube. 2x cubed minus 15x squared plus 36x. And then second derivative, we're just going to do the derivative of that. So that would be 6x squared minus 30x plus 36. I'm going to set that equal to 0. And then I'm going to go through and divide everything by 6 just to make the numbers a little bit smaller here. And then we can factor. So that's going to split into x minus 2 and x minus 3. And so I'll make a number line for each of these. If you're like, wow, this is a lot of work for a multiple choice question. Yeah, sometimes they're like this. But it was just a derivative and then factoring. So it went quick. So x minus 2 is going to change at 2. It'll be negative and then turn positive. Same thing for x minus 3. It'll change at 3. And so if you slice up your number line, a negative times a negative overall sign is going to be positive, and then in between 2 and 3, it'll be negative, and then above 3, it's going to be positive. At this point, I forgot what they were asking about. I knew it was concavity, but what was this? Concave down. All right, concave down, where the second derivative is negative, that's going to be between 2 and 3. And so that is D for that one. That was a good bit of writing for that problem, but I don't feel like that one was particularly hard. Like the derivative was simple, and then you just had 2 and 3, so the numbers weren't that awkward, but it was a little bit of work for that one. All right, number 9, we're given f of x equals this accumulation function. How many points? All right, so we're not going to actually find them, just how many are there? On the interval 0 to square root of pi, is the instantaneous rate of change. All right, so hey guys, what does instantaneous rate of change mean? Just in a single word. I'm going to keep you awake by asking you questions here. What is an instantaneous rate of change? Good, perfect. Nice job, guys. Derivative, awesome. You guys rock. All right. So when does the derivative equal the average rate of change? Which I already asked you guys that one today. That's slope. So we want derivative to equal slope. Does anyone remember what theorem this is? They didn't mention the theorem by name, but this is one of our important theorems that we did. Does anyone remember which one this is? Where we did instantaneous rate of change equals average rate of change? Good, nice job, nice job. Mean value theorem. Nice job, Anna, perfect. All right, mean value theorem. Always think mean means average, think average rate of change equals instantaneous rate of change. Anyway, we're gonna get the derivative. So let me get the derivative of this function. There's gonna be a chain rule for the x squared. So we're gonna have to chain on the derivative of x squared, which is 2x. And then I'm gonna plug the x squared in for t. All right, so that is our derivative. And then we need to get slope. So it's going to be slope from 0 to square root of pi. So I'm going to need points for 0 and square root of pi. And this is going to be really similar to the other problem we did. I don't remember what number it was, but we're just going to plug these values in and see what we get. Now 0 is going to be easy because if you do accumulated area from 0 to 0, that's just going to be 0. You haven't gone anywhere, so you get nothing. And then let's plug in square root of pi. So this will be math time, 0 to, now it's square root of pi, but then we're going to square that. So the squared and the square root cancel. That's just going to be pi, which again is right here. It's your exponent key. You just have to hit second. It's right below clear. So second exponent. And then sign of x. I know it says t, but I'm typing x. And then dx. And that gives you 2. Do you remember we talked about these with the trig functions where each little bump of it is worth 2? I think that's cool. Anyway, it comes out to just plain 2, which is neat. And then we're going to do the slope of those points. So slope would be 2 minus 0 over square root of pi minus 0, which would just be 2 over square root of pi. And so this is our derivative. This is our slope. We want to set them equal. So what I'm going to do is go into y equals, clear out what's in there. I'm going to put this in y1 and this in y2, and we're going to see how many times they meet up. Again, it just said how many points. You don't have to actually find them, just how many are there. All right, so I'm putting the derivative into y1 and then the slope into y2. Now, don't just hit graph. I am going to go to window. Oh, this is really weird because I zoomed in on something else. We want our window to be this interval that they gave us. So our interval should be from 0 until square root of pi. I'm not really worried about what the y's are. I'll just leave those -2.5 to 2.5 right now. I mean, it could really, you know what, I'll change it back to standard. We can do -10 to 10. That doesn't really matter as long as we can see the intersections. I just need the x's to be this 0 to square root of pi. And all we want is how many times they intersect. So here you go, guys. How many intersections do you see? That's our answer. How many have we got? Because that's really all they're asking for. Good, 2. Yeah, 1 right there and 1 right there. They didn't ask for them. We just need how many are there. So this one is C. All right, and the last one, function is given by this integral here. We want f prime of 2. I love ones that are like simple to answer, like f prime of 2, cool. I'm just gonna do the derivative and then plug in 2. It's not real complicated, like you don't have to interpret, it's just find f of 2. Like, cool, okay. And you have to go and do that, but at least the instructions are simple. Unlike this one, the instructions are kind of complicated. This one, at least you know what they're asking for. All right, so this derivative involves a chain rule. I'm going to chain on the derivative of 2x, which would be 2. And then you just have to plug 2x in for t. So actually, let me go ahead and square that. If you square 2x, that's going to be 4x squared. So that's our derivative, and we're just going to plug in 2. There's a lot of 2's in this problem. So this will be 2 times square root, let's see, 2 squared is 4, times 4 is 16, minus 2 times 2 would be 4. So that's 2 square root of 12. And they actually didn't split that. This would just be 2 square root of 12, which is e. Let me go through splitting that, though, because I'm actually really surprised that they didn't simplify that further. What would 12 split into? Like, what two numbers multiply together to give you 12 that you'd be able to reduce one of the roots? Yeah, good, good. 4 and 3. Oh, and you even wrote 2 times 2 times 3. Good, so square root of 4 is 2. And so you'd end up with 4 square root of 3. I'm actually really surprised that they did not make you do that. So anyway, for the sake of going through that, that's how you split up a root.